So hello everyone. Nice to see you. It's a long time. So this is I'm basically gonna give you the same seminar I gave at the first general meeting of this course action when I was now in September in Bari. So I hope I will remember what I need to say. And yeah, I'm part of this course action. I'm a management member of Estonia. And I was invited to give a review on the dark matter in the Milky Way. So I used the same. So basically what I said to them and I'm saying to you is that what I wanted with my review is to open a dialogue. So these people were particle physicists. So the idea that they wanted to discuss is open a dialogue to understand what are the wrong things we know about the distribution of dark matter in the Milky Way, and what are the best strategies to use our galaxy as a laboratory for testing the nature of dark matter. So this was the general idea. So what I said to them, and I said to you, is that I think we always need to be open-minded, because what we think might be true today might not be true in the future. So I wanted them, and I want you to enter this talk with an open mindedness. And in order to do this, in order to enter this mindset, let's very briefly review how the knowledge of our galaxy has changed along the years. So here you see the first map. Of course, this is a brief review of history and probably bias. So in here you can see the first chart we have from the Milky Way. At that time, everything was the Milky Way. So there were no galaxies out there, everything was the same. And this was, in this chart, every dot corresponds to a star. Every star in that time had the same intrinsic luminosity. So it was not known what was the intrinsic luminosity of the stars. It's assumed that all stars have the same intrinsic luminosity, but it was not known which was this value. So it was not known what was the scale of the galaxy. Okay, so but in any case, in this very first chart, the sun was located in the very center. Okay, so in 1920, so in the 19th century, photographic plates start to be used in astronomy. So this produces a big leap in our conception of the galaxy. And two models appeared about the galaxy in the 1920s, and we have the model by Kapteyn and the model by Shapley, so in the left and the right. So Kapteyn derived his model by counting the stars, and in his model, the Milky Way had the size of 10 kiloparsec, and the sun again was located close to the galactic center. In Shapley model was built using or measuring globular clusters, and by assuming that these globular clusters are spherically distributed around the galaxy, and he derived that the size of the galaxy was roughly 100 kiloparsec, and the sun was located 15 kiloparsec away from the galactic center. So both models were wrong, and the main reason for that is because it's not known until 1930 the role of interstellar extinction, dust obscuration. So this is only realized in the 1930s. Okay, so this milestone, the discovery of the importance of dust obscuration, together with the discovery of the 21 centimeter line, so the 21 centimeter is a perfect tool to map the neutral hydrogen in our galaxy. So these two things allowed galactic studies to mature. So we enter in the 1950s, in the 1960s, a more mature era for galactic studies. And in here, many models appears from the house. So we have the model by Kuzmin, and we have the model by Einasto. So two models of Einasto, also Japanese people were a lot of them. The idea is that all these models, what they had in common is that they were describing the 10 kiloparsecs, so the inner 10 kiloparsecs of the galaxy. So the inner 10 kiloparsecs was thought to be the boundary of the galaxy. So none of these models had a dark matter halo. And this is because, again, it's not until 1974 when it was proposed first in this paper, again by the house by Jan Einasto and Ensar and collaborators. So it was proposed, and later on by Austria in the USA. So it was proposed that galaxies live on a humongous halos of dark matter. Okay, so halos are started, so since the 1980s, people of the scientific community started accepting this idea that galaxies live in these humongous dark matter coronas, and many models of our galaxy appear with the dark matter halo. We have understood, or we have constrained what is the dark matter density in the solar neighborhood. Here you see a compilation of values. We have constrained what is the mass, the total mass of the halo. We have constrained what is the density distribution of the halo. So the general idea today, so what people commonly think of, is that we live on a spherical static halo of dark matter. And what I want to really push forward in here today is that neither of these assumptions are true. So we don't live on a static halo, we don't live on a spherical halo. So it seems. So, and what I want to do is to show to you the observational or empirical evidence, so we can discuss if this, what I'm saying, is correct or not. Okay, so first of all, let's discuss the first shortcoming I see in our understanding of the universe, which is the static dark matter halo. So thanks to Gaia satellite and to other spectroscopic surveys, we now see our galaxy as a complex system in evolution. You need to push hard.
It doesn't happen.
Very So the idea is thanks to the Gaia satellite, which I think it was launched in 2013, another, as I said, wide field spectroscopic surveys, we see our galaxy as a complex system in interaction with its environment, and it seems we cannot anymore forget about the environment. So we see, we know that the galaxy has collided with a dwarf asteroid, with a dwarf galaxy in the past, between 7 to 11 gigayears ago, and this collision with the Gaia Sausage Enceladus, you might have heard this name. So this collision really shaped our galaxy. And we have understood, or we have inferred the existence of this collision by observing a bimodality in the stellar halo of the Milky Way. We have observed a bimodality in the stellar population, in chemical composition, and we have observed a bimodality in the kinematics. So here in this plot, and probably stellar physics will know better than me. So here in this plot, it's clearly seen the bimodality. So you see that if you plot, this is the color magnitude diagram for the stellar halo, and if you plot with Gaia DR2, if I'm not mistaken, so if you plot the color magnitude diagrams, you see that you have two distinguishable stellar evolutionary tracks. So this is the first hint of the bimodality of the stellar halo, of this past merger with the Gaia Sausage Enceladus. The bimodality is also observed in kinematics, and what we observed is that the velocity, or the shape of the velocity ellipsoid, changes with metallicity. What we observed, as I'm showing in here, is that as you increase the metallicity of your sample, the amount of motion in the radial direction, so this is the velocity dispersion in the radial direction, which measures the amount of motion in the radial direction, it increases. So the stars move in radial orbits, or this amount of motion in the radial direction is larger than the amount of motion in the other two directions. Okay, and this is again a signature of this merger event with the Gaia Sausage Enceladus. Okay, so this is so in the stellar halo of our galaxy, we have evidence of this interaction with our environment. Now I'm going to talk about observational signatures of these interactions in the disk of our galaxy. So again, thanks to Gaia, we have access to large-scale maps of the stellar disk in the Milky Way. So you can observe these maps in here, and what you observe is that these maps things are not as smooth and stable as you would expect in a perfectly symmetric equilibrium stellar disk. There is a lot of things going on. So if we would live in a perfectly symmetric disk, you would expect not to see this inhomogeneities. Okay, so apart from these inhomogeneities in large scale maps, we also observe ridges in the rotational velocity versus galactocentric distance map plane. So you see this ridges in here. And we have observed phase space, so the famous phase space spirals, no, in the vertical velocity versus vertical direction plane. So these phase spirals basically are produced when you have a perturbation in the vertical direction and the subsequent phase space mixing back to equilibrium. So there are signatures of disequilibrium in the stellar disk of our galaxy. Okay, so the cool thing is that these peculiarities that we observed in the kinematics of the disk stars, they tell us messages, and we can go to simulations to try to understand what are these messages. For instance, the ridges has been proposed as the kinematic signature of the galactic bar, but there are other hypotheses. Another hypothesis is that these features are due to the interaction of our galaxy with the Sagittarius dwarf galaxy, for instance. But in any case, this is a hot topic in galaxy dynamics, and what I said to Cosmic Whispers people is that for us, for the astroparticle community, which is not you, what is important is that all these things seems to point out that we live in a disequilibrium galaxy. So the disk of our Milky Way is in disequilibrium, okay? And we use the motion of stars in the disk to infer the distribution of dark matter, as you see in this line here. So we have the astrophysical observable, we include our dynamical model, we obtain the dark matter distribution, which then inputs whatever so people that are looking for dark matter in the laboratory, or for instance in the galactic center through gamma rays, they take what we give to them in order to infer constraints on particle physics models beyond the standard model. What I was claiming is that in this dynamical modeling, we assume a steady state. We assume that the phase space distribution function of stars does not depend on time. And you have seen, so this is clearly showing that the phase space distribution is not constant with time. This is so we have suffered a perturbation in the vertical direction, and now we are facing, so we are mixing back to equilibrium. So, but the phase space distribution is not constant. So the big question, which I think needs to be answered, and I'm not the only one who thinks that, is that how much. Okay, we observed all these peculiarities in the Gaia data, but how much does this affect the dynamical modeling? So, or the modeling assumptions that we make, because we make the modeling assumptions of stationarity and of steady state. Okay, so this is the open question I was posing, and this is how first working package of my proposal.
How do you conclude?
And Annalina's PhD first year.
How do you conclude from that figure that it is not constant in time?
So because this, what people have derived is this is the signature. So what they have done, there are actually videos. So you have a population of stars, and then you perturb them in the vertical direction, so they are rotating and they are also wobbling a bit in the direction. And what you see is that they form this pattern in phase space. I personally think it's not trivial. So they have done it with the calculations. So, and also they have seen, maybe Ryan knows better, so they have also played this with harmonic oscillators. I have seen this. Okay. So it's the evolution path that you will you would observe this if you have a perturbation in the vertical direction. So you will observe these patterns in the kinematics of the stars.
Okay.
It's okay? Well, I was clear?
Yes.
But
We believe you.
you don't need to believe me. Leave that for church. So, maybe this, I need to take. So, okay, so what I pointed out is the first shortcoming is we don't know how stable the dark matter halo is. So, it's an open question. It's an open question in my mind also. So, and the second thing that I wanted to and it's not going. Not going. So the second thing that I wanted, the second shortcoming that I see in our conception of the dark matter halo is the sphericity. So it seems from, so normally what you think is that you have this spherical block in there and in the center you have the Milky Way. It seems like this is not true. What it seems that it's happening is that the shape, the three-dimensional shape is changing with radius. Okay, so for instance, and what it's thought it is that in the inner 20 kiloparsec, okay, in here I want to say that this take with a pinch of salt what I'm gonna say, because different groups arrive to different answers, okay? And there are several papers that arrive to the same answer, but all these papers are made by the same people. So I would say it's not known regarding the shape. It's not known beyond 20 kiloparsec, okay? Below 20 kiloparsec, which is the stellar disk, we know, or I think it's a good assumption to say that the dark matter halo is spherical. So people have measured this, different groups, different papers, and they all agree with a spherical dark matter halo in the inner 20 kiloparsec. They measured this by measuring tidal streams and modeling the formation of tidal streams. The most famous one, I would say, it's Palomar 5 and GD1, and also they have inferred the sphericity by modeling the Jeans equation, the stars, the halo stars. I forgot to say something about Jeans equation before, but okay, sorry. Let's continue. So they found out that the halo in the inner 20 kiloparsec is spherical. When we go beyond 20 kiloparsec, situation starts to be a bit complicated. I would say it's again a hot topic in galaxy dynamics, but it's not known. What it seems to happen is that, and in here, don't believe what I'm saying. So it seems that the dark matter halo is oblate. This is what all this more or less arrives to this conclusion. So it's oblate, and the minor axis has the same direction as the angular momentum of the Large Magellanic Cloud. Okay, but what they also say in the paper, I think it's this passage here, is that their results strongly depend on what are the input. So in order to, I forgot to say, so they derive these constraints by modeling the Sagittarius stream. Okay, so by modeling the Sagittarius stream, they can infer the sphericity of the dark matter halo. But in modeling the Sagittarius stream, it's highly non-trivial. You need to include the effect of the Large Magellanic Cloud, and you need to know what was the initial mass of the Sagittarius dwarf galaxy. So it is not known. There are uncertainties on what is the actual mass of the Sagittarius dwarf galaxy, the progenitor, and it is also not known what is the mass, the total mass of the Large Magellanic Cloud. Actually, there is a dichotomy between having a very light Large Magellanic Cloud or having a very heavy Large Magellanic Cloud. So the results, and they claim this, are very sensitive to these values of the Large Magellanic Cloud and the Sagittarius dwarf. So if these values change, the results will change. But what they claim is that you have this oblate with the minor axis parallel to the orbital plane of the Large Magellanic Cloud.
On the plot, it says prolate. Is it just a mistake or
What?
on the plot, like after the Gaia box, it's on a prolate side?
This has to do with what I said. I think this is Veracilo and Helmi. No, it cannot be. It's a
after
mistake.
Missed that one.
Because Veracilo and Helmi, actually what they found out is that it's prolate. So all these people find oblate and Veracilo and Helmi find prolate. And what they Veracilo and Helmi actually is this paper where they claim that we have a dark matter halo that changes, the shape changes with radius because otherwise it wouldn't be stable. And also this change of shape with radius is also observed in hydrodynamical cosmological simulations. Okay, but again, this is a hot topic, and I think it's still not known what is the shape of the dark matter halo, but there are possibilities to do things in there.
You just said that the changes in hydrodynamical simulations, is it something specific to those simulations or?
And I don't know. I would say it is.
Okay. So as
I
opposed
would
to
say it is.
just dark
I would
matter.
say, yeah, I would say it is. But I don't know, that's a good question. I don't know. Because I would expect that the baryons have a role in changing. So what I found interesting when preparing this talk is that I have seen many people now switching into self-interacting dark matter. Seems like self-interacting dark matter is gonna be the new cold dark matter. So I don't know, but I have seen many people advocated push forward a self-interacting dark matter. And what people have studied, although I would say the possibility of doing this is very, very low. So you can use the shape of the dark matter halo to constrain self-interactions in the dark matter sector. And this is because in self-interactive dark matter, and this is what I'm showing in this plot, I'm gonna show sitting here. So this is the axial ratio as a function of elliptical ratio. This is minor to major axis. Okay, one is spherical. Okay, so the closer to one, the more spherical. This is also the more spherical you are. So what it's observed in simulations, hydrodynamical simulations of cold dark matter and self-interacting dark matter, is that if dark matter is self-interacting, subhalos are on average spherical, more spherical in the outer regions of the galaxy, whether compared with their, say, cold dark matter counterparts. So the problem is that, and this can be understood by the fact that in so how I see this is that in cold dark matter, so the triaxiality of the dark matter halo reflects the position of the halo in the cosmic web. Now, what are the preferential directions of flowing material inside the halo? The thing with self-interacting dark matter is that you have self-interactions, and the exchange of angular momentum between particles is larger, so you erase, so exchange of energy is more efficient, so you are erasing the boundary conditions. And this is why in self-interacting dark matter, on average, you expect halos to be more spherical. The problem, and this is a bit misleading, this figure in here, is that they are just showing one case, but if you plot the halo to halo variation, if you do this exercise for many, many halos in simulations, so you basically are erasing the signal of self-interacting dark matter because the halo to halo scatter is much larger than the difference on. So I was saying on average, but when you account for stochasticity, you erase your signal. But in any case, what I wanted to say, and this is why I included this, because it was interesting for particle physicists, is that people have tried to use the shape of the Milky Way as a dynamical test for the crosstalk in the dark sector, dark matter sector. So here I started my personal publicity. So, so I wanted I think many of you have maybe already seen this slide many times, but let me remind to you once more. So this is part of the work I have done for my master, for my PhD thesis, and then some work that my current PhD student in Tallinn is doing. So what we have done is we have quantified what people, when I came back, no, I'm not gonna go. When people normally do in astroparticle communities, so when they need, in order to interpret the results, they need to understand what is the dark matter density distribution in the Milky Way. So what people normally do is they just take one value and they continue with their lives. Okay, so what we provided is a chi-square which quantifies, so we quantified into the final distribution of dark matter many sources of uncertainty. Okay, so I'm explaining myself very badly. So what we did is, let me explain a little bit more. So what we did is we James modeled the rotation velocities of the disk. This has been done many times in this house also. And in these two papers, we propose a frequentist analysis to propagate different sources of systematic uncertainty into the final distribution of dark matter. What I want to say is, for instance, so we are observing the rotation velocities. Okay, but we are observing velocities with respect to us, with respect to the sun. In order to play this game, you need to change reference frame. You need to change from heliocentric reference frames to a galactocentric reference frame. So in order to do this, you need to include what is the distance of the sun and what is the velocity of the sun. And these two quantities are unknown. So what we did is we take the uncertainty on these two quantities and we propagate into the final result. These are systematic sources of uncertainty into the final result. So we provided a chi-square which can be used to incorporate all these astrophysical uncertainties when you play your game or of interpreting the results of your favorite particle dark matter experiment. And this was quite successful, I would say. We got quite some citations in these papers, and this is the recent paper by Powder, and he did something similar but using a Bayesian approach. Okay, but in any case, if you want, okay, and the caveat in here, as I said, we use James modeling, assuming a steady state, which I have shown before that it seems not to be anymore true. So the question is, can we still use this, which seems to be wrong? And the answer is yes. And why is yes? And it's because we take into account, so the uncertainties in the final distribution of dark matter are quite large, especially not because of the sun's distance to the galactic center, although in here this is the main uncertainty. But in here what we found out is that the main uncertainty is the actual, we don't know what is the actual shape of baryons, so stars and gas. So because you apply James modeling, you derive the total gravitational potential, but you need to couple this with the Poisson equation in order to derive the dark matter, the dark matter density profile. So you need to subtract. No, we don't count. We need to subtract the stars and gas. Okay, so the question is, you can still use this because uncertainties are too large. The main source of uncertainty is our current no knowledge of what is the actual shape of the stars and gas in the galaxy, okay, which we also accounted in our work. So here I made an example, again, more publicity to myself. I gave an example of how to use the chi-square that we were providing in our previous plots. And in here, many of you have here, maybe not the new people. So there has been, I think in 2000, 14, it was 13, there has been a galactic center. So the Fermi satellite observed an excess of gamma rays coming from the galactic center. Okay, of course, this is very debatable. There are people that it's not due to, this was interpreted as dark matter annihilation, but there are other hypotheses, like you have a population of pulsars in the galactic center. So it's, I would say it's still an open question. And the main problem was that in order to interpret your signal, you need to account you need to introduce, or your signal depends the flux of gamma rays produced by dark matter annihilation depends on what is the dark matter density in the galactic center. And the density in the galactic center is uncertain. So what we showed in this paper, and there were many people claiming that, okay, if you assume the gamma ray excess is due to dark matter annihilation, you can constrain the annihilation cross-section versus dark matter mass. And what you found out is something, a mass of the wave of the order of 30 kiloparsec. And what people were complaining or saying is that this parameter space is excluded by upper limits from dwarf spheroidals. We don't see gamma ray excesses coming from dwarf spheroidals. Therefore, this is excluded. This cannot be due to dark matter. What we were saying is that, yeah, if you do the classical analysis where I do not take into account the effect that I don't know what is the actual shape of the dark matter in the galactic center, you obtain this very small blob. But when you account, you add to the galactic center excess analysis another chi-squared due to the rotation curve analysis. So it's something that accounts for the uncertainties. You find out that the region in the parameter space that you prefer is much larger. So the plane tension, it's not so clear. Also because this should be moved up and down because of uncertainty. So until now, I have been talking about the smooth dark matter density profile, but this is not the whole story. So we know that the dark matter halo, we expect a myriad of substructures or subhalos orbiting our own galaxy. And this is because structures are formed hierarchical, meaning that smaller structures form first, and larger structures, they form by merging of smaller structures and also by a small accretion of matter. Okay, so we expect a myriad of substructures orbiting the Milky Way, galaxies in general. So the interesting point is that the abundance of the population of these subhalos orbiting galaxies strongly depends on what is the nature of dark matter. Okay, so you can, if you are able to constrain the abundance of subhalos, you indirectly can constrain the dark matter nature. Okay, and this is because, for instance, if the dark matter is warm, so the mass of the dark matter is in the Kiwi, this means that in the early universe, this dark matter had a thermal energy, so it frees, so it erases the smaller structures. So, or if you have a fuzzy dark matter, you need to account for the wave effect of for the quantum effects of the dark matter, quantum pressure, although it's not pressure, but okay, quantum pressure, what people call quantum pressure, they also erase the Pauli blocking principle. No. So, so there are many strategies. People are trying to. Okay, what I wanted to say here is that you have these dark matter subhalos. The most massive of these subhalos, they are able to form stars in their interior, so they have a dwarf galaxy in their interior. Examples of this are the Large Magellanic Cloud or the Small Magellanic Cloud, but we expect subhalos with masses smaller than 10 to the 8 to be dark, so to don't have a luminous counterpart. As you can imagine, they don't have a luminous counterpart, so it's very difficult to detect them. Okay, so there are many strategies to detect these dark subhalos in our galaxy, and the strategies basically are to detect the dynamic signature or the kinematic signature of these subhalos. Okay, and in here I would say you can distinguish. You can look for signatures in the stellar phase space, and in here you can distinguish between looking for apparent perturbations. So these are perturbations that you have a dark subhalo produces microlensing or weak lensing, and you have apparent changes in the position and the velocity of subhalos. But you can also look for real perturbation. The idea is that you have subhalos that are moving through the galaxy. While moving through the galaxy, they encounter stars, and they interchange energy and momentum with these stars. So what it means is that you have this subhalo moving through the stellar halo of our galaxy, and it's going to change the phase-space distribution of the halo. So you can try to look for these perturbations in data. And this is actually what we have done mainly, or this is the PhD of Sven. So this is okay, what we have done mainly with Joseph Patten, clarified and Sven Powder. There are many people also involved, Ryan Kipper in here. And the idea is that we have tried to look for this, as I said, you have the subhalo moving through the galaxy. It interacts with the stars, and it leaves, as you see in this case, it leaves a characteristic scale, a characteristic trail, a stellar wake. So we try to look for this wake in Milky Way-like galaxies, in simulations of the Milky Way, using two very simple machine learning approaches. And what we found out is that, okay, I'm not going to enter into the details. I think many of you have seen this work many times, but the idea is we took 3 Milky Way-like galaxies from the fire to simulation. First, we found for subhalos by applying the Amiga halo finder. Once we identified subhalos, we classified the stars. We have our stars in our simulation, and we classified them as being perturbed by a subhalo or not being perturbed by a subhalo. So we have two populations of stars: ones that have been that interacted with a subhalo, and ones that have not interacted with a subhalo. Now the question that we try to answer is, can we separate between these two populations of stars? And what we found out is that actually yes. So what we concluded with this paper, and I'm going to explain this a little bit more, is that subhalos live as a statistically detectable signal in the particle kinematics of stars, or in the kinematics of or phase space distribution of star particles in simulations. Okay, so this was quite promising, because once you see in theory that you can, this is detectable, the next step is to go to observations, but wait a go. So how we did this is we applied to very simple machine learning algorithms, binary classification, and anomaly detection. So I'm not going to enter into the details. So the guru in machine learning is Joseph Patta, and soon to be also Sven Powder. But it was quite cool to learn a bit about machine learning. We were implementing an autoencoder, which is basically, for those of you that are gurus in machine learning, you have two neural networks. So you input into your algorithm like the real image, the phase space distribution of stars, of background stars. Remember that I have background and signal. So we train our algorithms only in background. We input into the algorithm the phase space distribution of background stars. We transform this 6D dimension into a latent space. This is what the first neural network does. So actually we decided to use a latent space which needs to be a smaller dimension of 3, but this is just by fine-tuning. And then you have another neural network that converts this latent space into a 6-dimensional space, which is an image of the input stars. So you have 6D, real 6D of background, and recover 6D. So you tweak your neural network, the weights in your neural network, until these two images match together. Okay, so what you see in here, this is the true, what I input, and this is what I recover. And I do this using background stars. What this means is that if signal stars, and I build, and I say, this is my test statistics. So if a signal star is introduced now in these trained algorithms, so the difference between the real 16 and the image is going to be much larger if these two populations of the stars are distinctive. Okay, so what we found out is that signal stars, as expected, stars that have interacted with a subhalo are on average have a larger test statistics, which is expected, than background stars. And we can use this to distinguish or to identify the signal stars. And what we said is that we are able to identify 80% of signal stars while misclassifying 15% of background stars as signal. Okay, so this was very promising. Ooh. And then we decided to go to observations, and rather than go to observations, we go to mock observations. So we went to Gaia mocks. From these simulations, the prior to simulations that we were using, what they did is they created mock catalogs that reproduce what Gaia would have seen if Gaia would be inside this galaxy. So we use this catalog to play the same game. What we found out is that we don't know what is going on. And the reason for this is because in generating these mock catalogs, there are many random effects that we are unable to control. For instance, we are unable to define the footprint, so you can get lucky or unlucky with the footprint of your Gaia satellite, and you can contain more or less subhalos. So what we decided to do, and this is work in progress, I hope soon to be published, is to go a state below. And what we are doing is that we are doing wind tunnel simulations. Really, what we are doing is we have this box, this cylinder of particles, and we throw a dark subhalo, a perturber in this subhalo, and we are training our algorithms to detect the stellar wakes in here. So work in progress. Yeah, we'll have 5 minutes. So, and I ended my talk in Paris by also mentioning some of other work I'm doing. So, and to them so this construction is about cosmic whispers. So whispers as dark matter candidates. I don't know if you have heard about, all of you for sure have heard about WIMPs, but maybe none of you have heard about WISPs. So the WISPs is a new dark matter candidate. You see here, and it stands for weakly interacting slim particles, which are particles by definition which has a mass smaller than 1 GeV. But when you go to all these meetings, it seems like people are only working on actions. So what I wanted to point out in here is that WISPs are more than actions, and actually exoplanets and brown dwarfs are new, exciting, and powerful detectors for WISPs. And I wanted to show some of the work I'm doing forever with Lynn and Smirnov. So Rebecca and Yuri, what they propose is to use exoplanets and brown dwarfs as detectors of WISPs. You have an exoplanet moving through the galaxy. We assume that the dark matter halo is made of dark matter particles. The exoplanet encounters a WISP, and this WISP starts interacting in the interior of the exoplanet, so it can be gravitationally captured. So with time, you start accumulating more WISPs. And what happens is that if the WISP is a type of self-interacting, it's gonna self-annihilating, it's gonna annihilate, producing a standard model products. These standard model products are absorbed by the system, and the system radiates so the temperature of the system increases. So what you expect is to observe exoplanets that have a temperature much larger than what expected from standard models. Okay, and the cool thing about this, okay, two things I want to say in here. Of course, using celestial bodies as dark matter detectors, this has been studied since the 1980s. I think you can find the first papers of people studying this, the astroparticle community. The novel idea in Riemann and Smirnov is to use statistics. So we expect like 100 billion brown dwarfs in our galaxy. Of course, we are not going to detect all of them, but even a small number, it gives you great statistics. Okay, and the cool thing about this fact of using exoplanets is that your signal depends on the amount of dark matter. So if the dark matter density profile is scarce as expected, you expect to observe that the temperature of exoplanets increases with a smaller galactocentric distance. So this will be a clear smoking gun of these things going on. But in any case, so you need to whatever the dark matter is, it can be in anywhere in here. So it should be smaller than 10 to the minus 22, otherwise we would have observed microscopic quantum effects and we have not. And you need to fit the dark matter into a dwarf galaxy. So you are seeing it's 90 orders of magnitude. So it's not easy task. It's find the needle in here. There is one. So it's just an exciting strategy, and the cool thing about this, and this is why it's interesting, is that according to Rebecca's guru, James Webb guru, he has said to us that James Webb is gonna detect on the order of 10 brown dwarfs in the inner kiloparsec of the galaxy. So what we are doing now is forever with them. So we are trying to understand. So, okay, so in order to play the game that I was explaining right now, you need to know what is the mass of the brown dwarfs, you need to know what is the radius, although the radius you can assume it's a Jupiter, it's the same radius as Jupiter, it's a good assumption, but there are many things that enter, and these are also coming from observations that have uncertainty. So the game that we are playing is that how many of these, taking into account what is going to be the sensitivity of estimating all these quantities with Nancy Roman, with James Webb, what is the probability that we will be able to see this signal if dark matter is a wisp that self-annihilates? Okay, and this is what we are doing. And here is my takeaway. The takeaway for you is that we have two shortcomings, I would say, in our understanding of the dark matter density profile in the Milky Way. First of all, we don't know. I think it needs to be understood how global determinations of dark matter using equilibrium dynamical models, whether these models are biased or not. This is the first thing I think we need to find out. And the second thing I think we need to find out is that what is the actual shape of the dark matter halo. And another important thing is that dark subhalos can be key to understand properties of dark matter. So if you go to any conference, you can say that there is people in that observatory looking for dark subhalos. And another thing I wanted to point out in here, and this was not in my time in Cosmic Whispers, but this is a slide from Diego Blas, which is a researcher in Barcelona. And this is one of the things we were discussing really in the general meeting. So for me, and he also agrees, so there's still lacking an understanding or a systematic study of what are the galaxy dynamical tests that can be used to test the dark matter. It's still a bit like missing. So what I really like what he mentioned is that you have the stars as laboratories. for fundamental physics. Something is missing for galaxy dynamics. So galaxies as laboratories for fundamental physics. It's something that we were discussing in the course general meeting. Yeah, so opportunities. And that's it. Ah, no, this is the end. Many of you are asking. Keep it in mind. Thank you.
And you're in a hurry, but still time for some questions.
I hope it was understandable, so I should have prepared, repeated to myself.
So, Katrin, also say that people online can also just speak up or write in the chat. Hi, Katrin.
You said before that cold dark matter will form spherical halos.
No, in cold dark matter you have triaxial halo.
Okay.
More so what?
Yeah, but if you instead of putting only cold dark matter, do you know what gives like other halos, other space?
I'm not understanding the question.
Like if you don't put cold dark matter, but put other.
Self-interacting, for instance. Yeah, this is what they were. I only know with self-interacting dark matter, and this is the study that they were doing. What they see is that if you put okay. I mentioned before. So for me, the triaxiality is simply a reflection of the position on which there's the halo. No, so you have matter is infalling from primordial from given directions, not for all directions. So this is kind of this is going to be reflected on the shape of the dark matter halo. The thing is that in self-interacting, since you have self-interactions between the dark matter particle, you can diffuse or you can interchange energy more efficiency. So these are the triaxiality is a reflection of boundary conditions, and self-interacting erase these boundary conditions slightly on average. So you see that for on average this is closer to 1.
Can I ask again?
What is
In the previous slide, you have the box for the Gaia results, and it's really the slide before that, yeah, the yellow box is really tightly around the ratio 1. And so in the next slide, where you have the different dark matter models, they're all below, the middle part of the galaxy, left side, yeah. The yellow box of the Gaia results is really close to 1, but on the next slide, when you have dark matter models, they're all below 1. So they the green with the Gaia results are.
That's a good point. I don't know. I think statistical. So this is the 1 sigma kilo to kilo variation. So in principle, you can have a chance.
Okay, so it's only 1 sigma. But what are these observational points here? The green one, that one.
This is some that I was including here, but I don't remember by heart which for this one.
But they are observations.
Yeah, these are observations.
Mm-hmm.
It can impact the latest as well. If there is minor to major axis, it cannot be around 1 in this one.
Minor to major. No, minor to major, it can be 1. Minor to major, if it's.
This is above 1. It's like the rotation axis to the longest axis. Something else.
So this is minor to major axis.
So the smaller axis over the bigger.
The smaller over the bigger.
And it can be over 1 because that would be, the minor would be larger than the major.
Yeah, but Okay, so what you can't see into it, yeah, true, so I need to change the name.
My question is very simple. So if you have a dark matter halo, can we assume that it's also spinning?
That's a question for Punya and to Elmo. So
Because
it should spin,
yeah,
but I don't know. Number.
technically it should spin, and if it should spin, it should be an oblate, right?
It should be?
An oblate shape. Right? I mean, how can it be a projectile if it's spherical?
But
Unless there.
I don't know.
You can have spin as well, of course.
Yeah, but it doesn't have to, like, if you have an elliptical galaxy, then
For
you
it,
may not have a bulk rotation.
but I think you can have prolate shapes that are rotating in a spin.
But everything which is spinning should have, and
But maybe there are other effects going on.
Yeah,
But for instance, you have,
can the other effect that can.
I would say that if you have interactions with other galaxies. So it's not only the rotation which is shaping your shape, but also, no?
Yeah, to complete what you asked. So, for example, it has been observed that spin differs depending on the position of the halo environment. So if you have halos that are located in voids, for example, which are under bands, then they spin slightly more slowly than halos located in clusters and superclusters because there are more interactions between halos there. And I was going to ask about this.
And also adding, it has also been observed prolate rotation in the smaller scales. So in dwarf galaxies, it has been observed that the spheroidal component is a prolate and it's rotating around this major axis in this case, which is the minor in this notation. So it has been observed this prolate rotation also at the smaller scales.
But I guess it's likely if it's prolate, the prolateness is not coming from the rotation rather but pressure. I think like the pressure is making it prolate, not the
It
rotation.
can be also due to the barrier disruptions, so we have
Yeah.
pressure interaction between other halos between themselves.
I think that there can be many things, but I agree with you that the most you think of a disk, no?
Specific kind of interaction to produce a rotation, which will not be like. In
Thinking
general,
of pure rotation.
yeah, but if you want a projection specifically, then it has to be a certain kind of angle that you get.
Yeah, but there is this, you can as a, think of some random motion.
Yeah.
Within this halo, some random motion. That is much higher than this rotation. So which is keeping this shape of
That
this
random motion happens in even galaxies or any other.
If you think of a halo, do not think it as a disk galaxy or a star. It's not, the particles are inside moving. It's mostly random, but there is some like rotation and movement that's not cancelled out. When you can say it's rotating slightly. But most of it's just particles going in and out. It's
The
not like a
shape
star.
is not determined by rotation.
No.
That is the.
But the shape cannot be determined then by also random motions.
It can be not determined.
Because
It can
Yeah.
be determined, it can be
It
not.
can.
Could this be maintained also if there is this self-interaction that we're talking about? I mean, there is a random motion, it will go with that, right? And you will be left with this something that's going in the limit will go like this.
But for forming self, you need to be dissipation.
Is it-
Also. You need to dissipate energy away.
Okay, so.
So you need to
if it's
have
an
some
active condition, then,
Yeah, if you have elastic, I think you cannot.
well, you're not getting at this.
Yeah,
If
yeah.
expect
I was thinking on a disk. You cannot if you are not dissipation. If you don't dissipate energy away.
But you would still go from, even if you started from prolate, you would go to prolate, probably.
It should be the primary.
I don't know, it's intuitive, I think, but I suppose,
Yeah, in the end. Finish?
I have a question, a heretic one, about last few slides, I think. So. Because I'm curious.
This one?
Now further,
On my,
even further,
this,
even further.
this, everything is wrong, eh?
Even further.
We are doing something.
I think there was one more, wasn't it?
One more.
Was there one more?
Yeah.
Yeah.
This is not
Exactly,
mine.
about
This
that
is not
slide.
mine. This is not-
And my question is,
this is Diego Velasco blame.
well, I'm actually asking about what is the consensus or kind of what is the scientist thinking in this field. There are some measurements, high resolution, high precision measurements of hot stars to determine the velocity rotational curve of the galaxy. Close to the solar, this radius, few kiloparsecs outside as well, and well, it has been claimed that the rotational curve is Keplerian.
This
And
paper,
without
if you are talking about this paper, we can have a seminar about this paper because I think these people should go back to physics school.
okay, this color,
We are-
Galatutino
To be honest, what?
is 4.
But I think we should discuss this paper because to be honest, I was reading it and I think there are fundamental things that are totally wrong.
It's a recent paper.
Well, it's a
No.
recent paper that has not been published and I hope no one will accept it. Well, publish.
There are 2 papers published
First of all,
a few
okay.
years ago already.
This is fantastic because I'm gonna show to you what we concluded in one paper in here. We make, I'm very proud of this, I said it every time I present it. What is our paper called? Bayesian estimation using
Shortcoming.
Yes, okay. There has been a recent paper, very where they claim they have detected the Keplerian rotation curve. I have been reading this paper, and I think these people should go back to physics school. In this paper, we estimated the rotation curve. In here, what we are doing, which is normally you use Jean's equation, and you so because you observe rotational velocities. One thing is rotational velocities, and another thing is circular velocities. Okay, but people are plotting normally. What they mean by rotation curve is the circular velocity curve. So the rotation velocity curve is what you obtain. The circular velocity curve is what you obtain after tweaking your data, meaning that you need to take your rotation velocity, assume circular orbits, that the stars move in circular orbits, that everything is a steady state, and you derive using Jean's equation your circular velocity curve. Okay, and this what has been found is that it's decreasing with time and with radius. I'm very proud of this. I'm gonna show. So we had this paper where we are using Jean's equation. We couple Jean's equation with a very simple asymmetric model of the galaxy, and we applied an MCMC approach to derive the rotation curve. So classically, this is just, you have your equation, you plug in numbers and you obtain. Now we are doing a fitting analysis in which we introduce as 3 parameters the R0, so for instance, the distance of the sun to the galactic center. Because the distance of the sun to the galactic center plays a pivotal role on this game. So the distances to your, distances to your stars, estimates of the distances to stars plays a pivotal role in playing this game of building the circular velocity curve. If you have your distances wrong, then you are observing, you are deriving a wrong rotation curve. Okay, what I did in here, and I plot in here, we had different distance estimates. We have 1 over parallax from Gaia. We have distance estimates from Baylor and Jones, which they use a Bayesian fitting, and we use distances from GSP4, okay, which is the Gaia using photometer. So these are different ways of deriving distances. GSP4 also uses a Bayesian analysis. So you need to introduce priors. Okay. So what you see in here is that if you plot, if this GSP4 distances were unbiased, you would observe that your stars will cluster around this 1-to-1 relation. But you clearly see that there is an underestimation in GSP4 distances. And this is the same for Baylor and Jones. Okay, so you are underestimating distances when stars that are farther to you. If you underestimate distances, when you convert proper motions into rotational velocities, you are going to underestimate your velocity curve. So what we are claiming in here, and I'm very proud of this, is that cautionary tale about distances. Okay, so what we show in here, this is the Keplerian that you were talking about. What we show in here is that if we use different, so Baylor and Jones, these are quality cuts. Okay, so we are cutting depending on what is the relative uncertainty in parallaxes. You see, if you start taking more and more precise, so you see in here, this is related, sorry. Are you still following?
Yeah.
So this is related with this. This is also quality cut. So if you start just taking in things that are more precise, measuring the parallax, you start reducing your bias, your underestimation of data. So what we see is that if we start increasing this, the quality cut, we start seeing that the actual, you see here, so the slope, you start not seeing anymore a decline. So when I start making quality cuts, things that are less underestimated, I start observing that the slope of the rotation curve actually can be compatible with 1. So I think people need to be careful when saying we have a Keplerian rotation curve in the network. I think this needs to be. I don't believe it. Right now, I wouldn't bet on we have a Keplerian. Might be, but I don't think we have the correct answer now.
Thank you.
And I need to go.